Hello! In this video, we will discuss the shader side implementation of our point light shadow mapping technique. Now that we have 6 different view projection matrices and technically 6 different shadow map textures, our shader side implementation will have to change from what we did with a directional light. For any given pixel, we will have to determine which of the 6 sets of data is the right one to use. With regards to the violet triangle in the picture, if we were testing one of its pixels for shadow mapping, which of the 6 matrices should we use? Positive or negative, X, Y, or Z? Hopefully you can see from the diagram that we would want to use the positive X matrix. So how did we decide that? And how can we map our decision-making process into usable code? One way to determine this would be to give our shader access to the 6 frustum objects defined by our projections. We could then do standard frustum collision routines to determine which of the 6 a given pixel was inside of. While this certainly would work, it is going to be more expensive than what we need. From looking at the diagram, you may have determined that we should use the positive X matrix because the triangle is on the positive X side of the light. This relationship is going to be much easier to test for in our shaders. When we do our lighting equations, we are likely getting a vector from the pixel being lit to the point light. This vector is often called to light. If we negate this to light vector, we can then test which of its X, Y, or Z components is the largest. And this will tell us which of the 6 matrices we should use. Here we will see some branching code to pick one of the 6 matrices, where X, Y, and Z are based on our 2 light vector components. This solution is fairly gross as it will require a lot of branching. The branching solution presented is fairly optimized. First, notice I am not doing a matrix multiply inside the branch. Instead, we use the branch to determine the index of the matrix that will be used afterwards. Also, once I determine which is the largest, X, Y, or Z, I do not branch on positive or negative. Instead, we use some Boolean math to update the matrix index. Even with these optimizations, this is still far from the best solution. We will actually be able to achieve the goal of determining if a pixel is in shadow for a point light without doing any additional matrix multiplies. For the directional light, we needed the light view projection matrix to determine both our depth from the light and the shadow map texture coordinates we should use to sample at and compare with our depth. For our point light, using a cube map for its shadow map, we can actually use the negated 2 light vector as our texture coordinates. No matrix multiply needed so far. We can actually use a dot product to determine our depth. Given a normalized direction and a vector from the source to the given object, dotting these vectors will give the linear depth to that object. In our case, the forward will be one of the 6 cardinal directions. If X was the forward, we would be dotting our 2 object vector with a vector equal to 1, 0, 0. this would just return the x component of the 2-object vector. In fact, whichever of our 6 directions we use, they will always return either the x, y, or z component. Since we know these dot products will just return one of the 3 components, and we determine which of the 6 directions to use by which component of 2 light is the largest, our depth is actually just whichever component of 2 light is the largest. We absolute value these components as we are always working in positive distances. While the new solution does not require any matrix multiplies, we have created a new problem. The depth we are creating is linear, while the depths stored in our shadow map are logarithmic. We cannot directly compare these values, but we can convert. Here we will see a formula for converting linear depth values to logarithmic ones. The plane x and plane y values are all based off the near and far clip planes of the matrix being used. In this case, that should be the point light's view projection matrix. Since the near and far clips are typically static, we pre-compute some of this math in the plane x and plane y values, so it does not need to be repeated per frame per pixel. Once we do this conversion, we will have a logarithmic depth value that can be used and compared with what is stored in our shadow map. In the next video, we will be discussing 2 very common shadow mapping artifacts, both with silly names being shadow acne and Peter Panning.